Back to PaperCast, the podcast where we discuss cutting-edge research papers in the field of artificial intelligence. I am Justin, your host, and with me today is Emma, our PhD student co-host today. So we will be diving into episode number 4, where we will discuss a seminal paper titled Sequence to Sequence Learning with Neural Networks by Ilya Sutskever, Orio, Vinyals, and Quoc V. So basically this team, so interesting. And so why is it so in with the idea?
Thanks, Justin. The main idea of this paper is to introduce a general end-to-end approach for sequence learning using multi-layered, long short-term memory L-system networks, unlike traditional methods, which often require considerable pre-processing and feature engineering. So this approach learns to map sequences to sequences directly, making minimal assumptions about the sequence structure. So basically, this is particularly interesting because it addresses complex tasks like machine translation.
That's a great summary. Let's start with how LCI handles long sentences differently from traditional methods. So how does it actually manage this?
Like traditional methods, such as phrase-based like statistical machine translation like seminal systems, often struggle with long sentences due to their reliance on fixed length context windows. LSTMs, on the other hand, can actually maintain information over longer periods due to their architecture, which includes gates that regulate the flow of information. So this allows LCMs to capture long-range dependencies more effectively, making them really well suited for tasks involving really long sentences.
So interesting. The paper also mentions that reversing the order of words in the source sentences improves LSTM performance. So what impact does this have?
So reversing the word order in the source sentences introduces many short-term dependencies between the source and target sentences, so making the optimization problem easier for the LSTM. So this trick significantly improves the Model S performance by reducing the minimum time lag between corresponding words in the source and target sequences, which helps the LSTM establish better sort of connections between them.
That's quite a clever trick. So speaking of sequences, how does the LSTM handle out of vocabulary words in sequence translation? Can it actually manage them effectively?
So the LSTM uses a fixed vocabulary, and any out of vocabulary words are replaced with a special N token. So while this does introduce some limitations, the LSTM can still manage to produce sensible translations. So the paper notes that the blue score was actually penalized for out of vocabulary words, but the system still outperformed phrase-based stimulate systems, just indicating its really robustness.
So let's talk about the blue score. How does the LSTM's blue score compare to phrase like based estimate?
So on the WIMIT 14 English to French translation task, the LSTM achieved a blue score of 34.8. compared to a blue score of 33.3 for the phrase-based semit system. So basically, this just demonstrates that the LSTM can outperform traditional semit systems, even with a relatively unoptimized architecture and a fixed kind of vocabulary.
That's really impressive. So the paper also discusses multi-layered LSTM. What are the benefits of using multi-layered LSTM in sequence learning?
Like multi-layered LSTMs, so significantly outperform shallow LSTMs due to their ability to capture more complex patterns in the data. So each additional layer allows the network to create richer and more abstract representations of the input sequence, leading to better performance on tasks like machine-like translation.
So another interesting point is the re-ranking of system outputs. So how does LCN re-ranking improve SMIT system performance?
So the LCN can be used to rescore the hypotheses generated by the Sharmot system. So by combining the SMIT system score with the LCN score, the overall blue score improves. In this case, the LCN re-ranked the 1,000 best lists from the SMIT system. So just boosting the blue score to like 36.5, which was pretty close to the previous best for this task.
So finally, what assumptions does the proposed sequence learning method make?
So the method makes minimal assumptions about the whole sequence structure. So it assumes that the input sequence can be mapped to a fixed dimensional vector representation, which can then be decoded into the target sequence. So this flexibility allows it to be applied to a really wide range of sequence tasks without the need for extensive pre-processing or feature engineering.
That's very insightful. So, Emma, this paper has certainly paved the way for a lot of advancements in sequence learning and neural machine translation. So, for our listeners, this podcast is generated by AI using ChatTTS and is always for research purposes only. We always encourage you to read the original article and explore more.